lecture, we had studied the mechanism of the nucleophilic substitution reaction and the optical activity. In the last lecture, we had also studied the difference between the unimolecular nucleophilic substitution reaction and the bimolecular nucleophilic substitution reaction. So we had done the substitution reaction of the haloalkanes. Now in that particular series where we were studying the chemical properties of haloalkanes, we have one more reaction to go, and that is the Wurtz reaction. In Wurtz reaction, we take the alkyl halide and we react that alkyl halide with sodium metal, and there is a presence of dry ether, and the product which will be formed is they will be giving us higher alkanes. So if I take, suppose, if I write the reaction, it is alkyl halide plus sodium metal. The catalyst is dry ether and it will form RR plus NaX. For this I need two molecules both the sides. And if I take an example, suppose I have methyl chloride, I have two molecules of methyl chloride, two molecules of sodium. I react it in the presence of dry ether. I will have CH3 plus twice of NaCl, and this is ethane. So from methyl chloride we are getting ethane. That is, there was only one carbon in the reactant molecule, but whereas we talk about the product, we now have two molecules or two atoms of carbon. Here we had only one carbon. Now in one single compound we have two carbons. That is, the number of carbon has just doubled in the product. So this reaction is Ascent of Series. That is where we can increase the number of carbon atoms. Whichsoever will be the number of carbon atoms in the reactant, we will just have the double number of carbons in the product. So this is an Ascent of Series. So now we will switch on to the second point of this, or the second part of this chapter, that is the haloarenes. Okay. So first we will see the method of preparation of haloarene. Like we had done in the alkyl halides or haloalkanes, first method will be the direct halogenation. Okay, so we directly take an aromatic compound and we will do its halogenation. So we take benzene here, and that benzene is halogenated with, suppose, chlorine or bromine, and we react this in the presence of anhydrous FeCl3, and there is a specific temperature range of 310 to 320 Kelvin. That is, when we take benzene, we have the catalyst anhydrous FeCl3. The temperature range is 310 to 320 Kelvin. We will have chlorobenzene here. So this is the method of direct halogenation. The second method is by the Sand-Mears reaction. That is, now we are going to study a name reaction that is haloarenes by the diazonium salts. When I suppose take the second method is Sandmeyer reaction. Here we take benzene diazonium chloride. So if you remember the name, you can make the formula. It is benzene, diazo is N triple bond N and chloride is Cl. So this is BDC, benzene diazonium chloride. When it is reacted with an acidified solution of CuCl, it forms chloro or bromobenzene. That is, if we take benzene diazonium chloride, we will have a chlorobenzene, or likewise we will have a bromobenzene also. So these were basically the two methods of preparation of haloarenes. Now we directly switch off to the chemical properties of haloarenes. For the chemical properties, the first which we are going to study is the Fittig reaction. This is very much similar to the Woods reaction which we had done for the alkyl halides or haloalkanes. That is, in Woods reaction we used to take alkyl halides. Okay, so here we can just see that here we had alkyl halide, or we can say here we had haloalkane. Here we take haloarene. That is, we will have aryl halides. Suppose I take chlorobenzene, 2 molecules of chlorobenzene. All the other things will be just similar to the Woods reaction. That is, we will react it with sodium in the presence of dry ether. Now again, we will see that this chlorine along with this Na molecule forms twice of NaCl, and these two phenyl rings are now joined. So we get biphenyl. That is, when we talk about the Fittig reaction, we will take aryl halides or haloarenes. We will react it with sodium in the presence of dry ether, and we will have biphenyls. That is, now also you can see that the number of carbon has just doubled from the reactant which we had taken here. So the basic difference between Fittig reaction and Woods reaction is that in the Fittig reaction we take haloarenes, whereas in Woods reaction we take haloalkanes or alkyl halides, and here we take the aryl halides. The next reaction, it is a mix of these two. That is, the next reaction is the Woods and the Fittig reaction. That is, the second one is Woods Fittig reaction. Okay, so Woods reaction we had alkyl halide. So we will have an alkyl twice of Na, or if you wish we can rearrange this and write so that it becomes easy to just remember this. That is, we can write twice of Na plus, and here we have the presence of dry ether. Now we have seen that this part will go off. That is, one thing which will be formed is twice of NaCl, and this particular ethyl group will be joined to this benzene ring. That is, now we will have this ethyl benzene. But here the number of carbon has not doubled, but it has increased by 2 or by 1 or by 3, any which things which you take as an alkyl halide over here. So these were the two chemical reactions. Now the important thing which we study in the aryl halides or the haloarene is the electrophilic substitution reaction. And this electrophilic substitution reaction is common, almost common in phenols, carboxylic acids and aldehydes also. So let's start with the electrophilic substitution reaction. We are going to do it in one single step, and I hope that you will understand this thing. Suppose if I have a chlorobenzene, we have seen that whenever there is a group attached to the benzene ring, it is either ortho-directing, para-directing or meta-directing in nature. We know that these are the ortho position, this is the para, and these are the meta position. This position, para position, is already occupied by the group or the functional group. So now there are few groups which direct the electron density towards the ortho or para position, and there are certain groups which direct these towards the meta position. That is, they direct the electron density or the coming group towards the meta position. So when it is directed to the ortho and para position, the group is known as ortho and para directing in nature. And when the group present on the top of the benzene ring directs the incoming group towards the meta position, it is known as meta directing in nature. So chlorine is ortho and para directing in nature. So whenever there will be any incoming group, it will be directed to the ortho and the para positions. So now let's start with this electrophilic substitution reaction. So first we will do the halogenation. We can take chlorine or bromine or iodine, whichever group we want to introduce. So I have reacted with chlorine. We will have the conditions of anhydrous Cl3, and now when I add this chlorine on this, the product which will be formed is a mixture of ortho and para substituted products. Okay, so one will be ortho substituted and one will be the para substituted. This is the ortho substituted, this is the para substituted. This is 1,2 dichlorobenzene, this is 1,4 dichlorobenzene. The ortho product is minor, that it will be formed in small quantity, and the para product is major product, that is it will be formed in a large quantity. The next thing which we do here is the nitration. That is, when we are talking about nitration, we will introduce the NO2 group on the benzene ring. We will react it with HNO3 in the presence of concentrated sulfuric acid. So, I'll again have two substitutions, that is, I'll have two products formed. One will be the ortho substituted, likewise the other will be the para substituted. Again, the para substituted product will be formed in the major quantity. So can anybody just, or I wish you will be able to write the names of these two products. Now the third one is the sulfonation. When we talk about sulfonation, we will introduce the SO3H group, and the condition will be this will react with the concentrated H2SO4. Again, we have two products. The one will be ortho substituted and the other will be the para substituted. This is 2-chlorobenzene sulfonic acid and this is 4-chlorobenzene sulfonic acid. Apart from these three, we have the Friedel-Crafts alkylation and the Friedel-Crafts acylation. That is, will introduce an alkyl group and an acyl group in this chlorobenzene. So if I talk about Friedel-Crafts alkylation, I will introduce an alkyl group. So that can be any and it will always be in the presence of anhydrous AlCl3. Suppose I reacted with CH3Cl. Okay. Or suppose I want to introduce any other alkyl group here. The product will be the ortho and the para substituted chlorobenzene. So we have this Cl, one will be the ortho substituted, for I am taking CH3 group here. Okay. And the other will be the para substituted. This is 1-chlorotoluene, this is 4-chlorotoluene. You can use CH3 or you can use Br or any other halogen group here. The next part is the Friedel-Crafts acylation, and this acyl group is COR. R means any alkyl group you can use here. Here I will react this chlorobenzene with CH3COCl. Okay. So now the product which will be formed are ortho substituted, that is this Cl will go along with the hydrogen of this position and this will be COCH3 plus we will have COCH3. Now when we have this structure, it is named as acetophenone because this is a ketone group. Here we have the first carbon compound, here we have phenyl, so this is named as acetophenone. So This compound is called 1-acetophenone. This is the ortho substituted, and this is 1, 2, 3, 4. This is 4-acetophenone. So these are basically the chemical reactions of the aryl halides or the haloarenes. With this part, we end up with this chapter because the polyhalogen compounds and the uses of those particular polyhalogen compounds have been eliminated from the syllabus. So we end this particular portion here. That is, this is all for the first chapter of our organic chemistry. From the next lectures, we will be starting off with the next chapter of organic chemistry, that is alcohol